Boolean algebra is the foundation to understanding how a computer performs operations. Now, if B is a set with the binary operations plus and dot, because these operations operate on two elements in the set, and we have a unary operation that operates on a single element in the set, and we have two special elements, 0 and 1, which are elements of B, and this is a Boolean algebra if it satisfies the following axioms or rules. So similar to the rules that are satisfied in algebra for all the real numbers, but in Boolean algebra, our set is finite. And a typical example of this set is the set with the elements 0 and 1, because computers only understand zeros and ones, or on or off switches, to perform operations. So this is a typical set that we'll be dealing with. And in computing, the plus operation is an OR, the dot operation is an and the dash is a complement. So for example, you can visualize 1 as true or on, and 0 as false or off. And an example of an OR operation is true or false will give true, because either one of these has to be true. But 1 and false is false, because both of these have to be true for the AND operator to evaluate the true. And with the complements, we have the complement of 0 is 1, and the complement of 1 is 0. And we won't prove all of these axioms to verify that this is a Boolean algebra, but we'll just go through to prove this associative law using what is known as a truth table, which breaks up these complex expressions to simplify evaluating them. So note that our set that we had consists of the binary digits 0 and 1. So if we choose a number from this set 3 times, by the multiplication rule, we'll have 2 by 2 by 2 possible ways to choose those numbers, which we'll list here. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So given we're proving this associative law, we're going to break this up into y and z, and x and y, and evaluate the entire expression in the last 2 columns. So y and z is 0 and 0, which gives 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 1. And I encourage you to pause the video and do the remaining columns. So now let's proceed with x and y. So 0 and 0 is 0. 0 and 0 is 0. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1. And 1 and 1 is 1. So now that we evaluated y and z, we can evaluate x and y and z using this column and this column. So we have 0 and 0 is 0. 0 and 0 is 0. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0, 1 and 0 is 0, and 1 and 1 is 1. And similarly, we've already done x and y, which is this column. So we have x and y and z using these two columns. So 0 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. So as we can see, these expressions are equal for all of these possible permutations of the binary digits x, y, and z. So that proves that this associative law is satisfied. And in addition, we can see that the closure property is also satisfied because the numbers resulting from all the operations are 0 and 1, which are elements of our set B.